How can we hear sound when we cannot see the sound player? This is because the sound waves bend around the corners to reach our ears. This phenomenon of bending of waves around an obstacle in their path is known as diffraction. All types of waves exhibit this phenomenon. Observe the diffraction of water waves at a narrow slit placed on its path. When the size of the slit is large, the diffraction of water waves is quite negligible. On the other hand, when the size of the slit is very small, we observe the diffraction of water waves very clearly. The diffraction of waves depends on its wavelengths. If the size of the obstacle or the slit is of the order of the wavelength of incident waves, then diffraction occurs. This condition is also applicable to light waves. The wavelength of visible light is in the range of 400 to 800 nanometer. Since the wavelength of visible light is much smaller than the dimensions of most of the obstacles it encounters, we usually do not observe any diffraction. If a screen is placed behind an opaque object, light from the point source travels in a straight line and forms a shadow on the screen. But if we look at the shadow closely, we observe that no sharp boundary exists between the shadowed and the illuminated regions. The illuminated region above the shadow of the object contains alternate bright and dark fringes because of diffraction of light, and the pattern is called diffraction pattern. Let us now study diffraction of light at a narrow slit. Place a monochromatic light source on one side and a screen on the other side of a narrow slit. When the slit is illuminated by monochromatic light, a diffraction pattern is formed on the screen. The diffraction pattern consists of a central bright band, which may be much broader than the width of the slit, with alternate dark and bright bands on both sides. The intensity of the fringes decreases very rapidly. Let us now analyze the diffraction pattern mathematically. We represent light as a beam of rays.